Great. Good afternoon, everyone. So yeah, my name is Redouane Lguensat. I'm coming from the Institut Pierre-Simon Laplace in the Climate Modeling Center of IPSL at Sorbonne University in Paris. And I'm also affiliated with the IRD, the French National Research Institute for Sustainable Development. IRD is actually a French, it's Institut de Recherche pour le Développement. And I'm very happy to be here. Always a pleasure to give talks at home. So thanks to the organizers. So today I would like to give you an overview actually with my personal experience of AI applications in climate modeling. But a disclaimer first, I hold a PhD in computer vision. I'm coming from the machine learning community. So I really came from this particular community and started to work first with oceanographers and then with climate modelers. But of course, if you have questions that are more related to the physical science, you can ask them to me. I'm very actually lucky to be surrounded by great and world-class researchers in climate modeling, and I can of course send them the questions and give you the answer right away. So yeah, before starting, I want just to remind you, if you don't know, that last year, the Nobel Prize in Physics was very special to climate modelers. It was very special, particularly to the IPSL also and to the other climate modeling centers, because it was given to 3 researchers. 2 of them, Manabe and Hasselman, were climate modelers. This is the first time actually that Nobel Prizes were given to climate modelers. And it was a big, big event. For the information, some of my colleagues worked with Manabe. Some other of my colleagues had PhD supervisors that worked under Hasselman, for example. So it was like a very big event at the climate modeling community. To give you just a small example of what this contribution of climate modelers and this recognition means to the climate modeling community, I can give you here a very old work from the 60s, the end of the 60s, from Manabe. That's a recent picture of Manabe. And he worked with his collaborators on a simplified atmospheric model that showed that if you double or multiply by 4 the quantity of CO2, which is a greenhouse gas, you can actually find with a climate simulation. So when I talk about climate models, you can just think about a computer simulation, okay? So they did find actually that the temperature at the surface starts to increase, okay? So climate models, I mean, even simplistic ones from the end of the 60s, did start showing this climate change effect on temperature, for example. So what is the current, situation right now? We do have what we call CMIP6 models. I will not get a lot into details, but if you want to have an idea, CMIP6 models are an ensemble of more than 100 climate models, okay, coming from 49 climate modeling centers around the world. Unfortunately, down to climate models, coming really from Africa for right now, and I hope this will come in the future. So we do have 49 climate modeling centers around the world. Each center give a number of climate models, and then we group them all. And this is what we call the CMIP6. It's an exercise. I can give you more details later. And then what we do with all this human knowledge coming from all these models, we actually aggregate them and see, for example, for the temperature. Of course, we can do it for other variables, but for the temperature, we can do projections in the future. Not, for example, I was here at the last presentation. It was more about weather. In climate, we are more interested in projections. After 10 years, 20 years, even after 100 years, etc. And what we see with the models we have today, that again, they show that the temperature, the trend of the temperature is increasing again. You do see different scenarios, what we call scenarios. For example, the worst scenarios, the red one is the scenario business as usual. If you don't do anything, if we keep doing what we do right now in the world, and other scenarios if we reduce the emissions of CO2, okay? So that was just like a very short intro. I'm trying just to give you some information, some quick information about climate change, the situation, and how to get information about it. So if you want to get information, more info about the state of climate modeling, about the climate change effect on Earth, on planet Earth, IPCC is the group, the Intergovernmental Panel on Climate Change, which actually produces reports for decision makers, reports for scientists, and also reports for all. The summary for all here. It's accessible, of course, it's free, you can check it, and it's really very simplified, this one. So I can share the slides later and you can check it. But I wanted just to mention Abdallah Moqsit. He's from Morocco. He's the secretary of the IPCC, so I'm personally proud of him. So this video is very nice. You can check it later. It's a 2-minute video that explains what is the IPCC. But in few words, a lot of in a voluntary basis, researchers come and try to summarize all the papers on climate modeling, on climate change, etc., and summarize all these papers, thousands of papers in a report. So this is really a big work. And the last report was actually published. There are several reports from the IPCC. One of them, which is really on the physical basis, physical science. It was published last year, 9 August 2021. And what was happening at 9 August 2021? Messi joined PSG, and you can imagine which news got a lot of coverage. I'll just skip the video. This presentation is organized into 4 parts. The first part will be very quick because this is actually a little bit my experience with doing machine learning climate science. When I started collaborating with climate scientists, I found that there is a problem of communication, and I'll explain to you what I mean. The thing is, machine learning is not new. I think you know, all of you, that machine learning is not something new. I mean, even linear regression is a machine learning algorithm. So what I found is that climate scientists, people working in atmospheric science, oceanography, etc., they already use some techniques for machine learning, but with other names. One main example is EOFs, for example, empirical orthogonal functions, which were developed independently by a meteorologist, Edward Lorenz, from the butterfly effect. And actually, the equations are the same as PCA, okay? So I started talking and collaborating with people. They started talking to me about EOFs, etc., for dimensionality reduction. I was thinking this is a new algorithm, but then I discovered that it's just PCA. So this, this miscommunication is sometimes makes, you lose some energy just to understand what the others do from the other community. So it's very important to take your time and check if the methods you are suggesting, probably they are already used by climate modelers. Quickly, analog methods. The analog methods are very popular in meteorology too. For example, if you want to forecast temperature tomorrow, you can take, for example, in a specific position, the temperature today, and look in a database for similar situations in the past. They call this analogs, and then check what happened next in the past and aggregate the information, and you can have a forecast for the future. So, well, analog methods, if you are informed machine learning community, this is k-nearest neighbors. Then Kriging. Kriging is used for missing data interpolation, and it's closely related to Gaussian process regression, which is a node school and a very classical machine learning algorithm. And then this is a more advanced example. It was a bit hard to discover it, actually. So climate modelers, they do, Suman mentioned data assimilation. In data assimilation, one of the technique from data assimilation, you need to do an optimization, and to do an optimization with gradient descent, etc., you need to have, you need to backpropagate gradients, all right? So you need to have a differentiable model. But the models we use in climate modeling are not differentiable, unfortunately. So what were climate modeling doing is they were actually writing derivatives by hand, which is a task, a very difficult task. So no automatic differentiation, that's what I mean. So the backpropagation, that was called adjoint modeling. But backpropagation is the idea of using, for example, automatic differentiation to train neural nets. So there are, I mean, connection between the two teams. There's a question. Yeah. I mean, it's just a computer science. I mean, a problem here because the models are written in Fortran, for example, and to do automatic differentiation for now there aren't, I mean, tools to do it with Fortran, except if you yeah, there were some other works where you try to just submit the code of Fortran and they generate the derivatives, for example, the adjoint. The functions are smooth and the models are yeah. So some examples of old works from Institute of Pierre-Simon Laplace. They were doing machine learning for a long time. Well, they didn't know about it. This is what is a bit funny because actually they talk about using techniques, but they don't call this machine learning. That's what I mean. Even, well, machine learning was not really the term used, in the end of the 90s. But yeah, they use techniques of machine learning, but still now they don't really use the word machine learning. So those some examples I really liked. For example, a conference paper even from NeurIPS 91 coming from the IPSL. So that was really, I mean, surprising for me coming from the machine learning community. So yeah, my message here for this part was just to say that machine learning is not new for climate science, but what is new is, of course, the recent deep learning revolution. So this revolution really attracted more machine learners to the field. So before talking about machine learning, of course, we need to talk about data. So for climate model data, as I said, climate models are like computer simulations, okay? So they are based on equations. So these are the primitive equations. No need to enter a lot in details here, but the goal is to try to reproduce planet Earth, okay? To reproduce all the processes happening in planet Earth. So you use a specific grid and you can have some refined mesh in some places of the Earth and less refined in others. So there are a lot of numerical modeling happening in this field. So we get concretely Fortran again codes that we run, and we get the data. We run them for some time to do something. For example, projections that takes a lot of time. You need a lot of, I mean, computing power. Takes a lot of execution time. Sometimes even going to weeks to get just one simulation, and even more. So this is how you get really your data set. And the data set are open, okay? The data set are open. If you are interested, I can send it to you. All of these actually are works that are open, that are accessible. Yeah, sorry.
So this distinction wasn't actually clear to me until maybe recently. I don't know if you have slides for this later. Mm-hmm. What are the types of questions that you would ask in climate that you wouldn't necessarily ask in weather? Like, what would you ask in like climate projections?
I mean, for example, projections, climate projection. That's really, for example, the first question. What will happen, for example, in a specific scenario after 50 years in a specific region, for example? Then weather forecasting is more short-term forecasting. And for example, cannot do reanalysis, I mean, with climate models because we don't have observations of the future. You see, so that's, for example, one of the questions. Don't know if you.
Yeah, I mean, yeah, no, I mean, so I guess, do you care about like long-term averages?
Yes, exactly. Yeah, exactly. Yeah, of course.
Maybe to complement the question, do you integrate interventions like policies, like the effect of policies on this?
That's what we call here scenarios. So we can actually add them. Well, there are specific ways to add them. For example, the simplest one is adding CO2, as I mentioned before, or maybe reducing or respecting the Paris Accords, for example. Yeah, you can. So there are specific scenarios that were discussed by the IPCC panel, etc., so that all the climate modeling centers in the world do the same climate models with the same different scenarios, and they can compare them all.
Is all the data synthetic from models, or we have also historical observation?
Here I'm talking really pure models, so no observations. So the observations are used, for example, to validate. Okay, so you run your model and then you validate with observation. Okay.
But for instance, do you take situation in 19,000 and you validate 80 years later because you know what was in the 80s?
Yeah,
and
yeah, yeah. So yeah, there is an initialization, yeah, where we take some climatological mean, for example, of temperature, and then there is the period of spin up, that takes some time, and then you run your model until you start approaching the periods where we have observations, and then you use some metrics to see if your model is going to the right direction. The spin up actually is like a really it's intrinsic from numerical models. Sometimes when you go from an initial point which is very far from your attractor, the attractor of your physics, you take a lot of time until you go to the attractor of your physics. For example, if you know the Lorentz model, for example, the butterfly effect, have you heard about it? Yeah, this is a very simple way to see it, but you can, you can imagine it like that. You need some time actually to get to a space where you have your physics and you start getting into real physics. So yeah, that's the spin. Okay, so now for the two parts left, I selected actually two applications. I worked on them that can show to you how climate models can be used in a processing manner. So we already have the data and we want to use the data for some specific applications. And another application I'll show later where you can use AI and machine learning for the model development itself. So for the first application, this was actually a collaboration with an oceanographer. And the goal here was to cluster ocean regimes. I'll try to be very quick here. So my colleague, Michael Sonwald from Princeton University did publish a paper in 2019 where she used the barotropic vorticity equation. No need to enter into details here. Just you can just see the 5 terms in the equation at the bottom here. So these terms were actually calculated for each grid point from the globe. Okay, each longitude, latitude, position from the planet Earth, she did calculate 5 terms. Okay, so what was the goal? The goal was actually to try to ask the question: if we have this 5-dimensional space, okay, this is a really easy application. Okay, you have a 5-dimensional space. Okay, each point has a 5-dimensional vector, and you want to search for some clusters. Okay, in an unsupervised learning way, you can, for example, use k-means, very classic and popular clustering technique, and that's what she did with her collaborators, and she got these clusters here. Okay, as 6 clusters. I don't know why okay. So she got 6 clusters here, which was quite surprising and very interesting because the clusters doesn't look like anything. I mean, they look like something very, localized. And a big part of her work and her collaborators, of course, was to, try to explain each of the clusters and interpret each of the clusters. So she didn't just use k-means and that's it. So she tried really to explain the clusters. And she found, these 6 clusters. So this is just a short intro. Why? I met her in 2019 in a conference, and actually she asked me the following question. She wanted to apply the same technique, but for other CMIP6 models. Okay, the first model, it was called ECHO. Well, it's a model called ECHO. Okay, she could write this equation, but for the CMIP6 model, physically it was very difficult, nearly impossible to write the 5 terms. but she wanted to apply the k-means for the other models. So yeah, sorry. Yeah. Yeah, physical quantities. Yeah. Yeah, actually, she actually took some equations here, the momentum equation, and she actually calculated them and did a mean over, for example, 20 years. Okay, so she did actually calculate them on the on a trajectory. It's a time series. Okay, it's a time series, and then she got these quantities for each position for the whole, for example, 20 years. Yeah. Read data, what do you mean by yeah, we don't have observations. Yeah, we don't have actually observations for the quantities. That's why. So this is really the realm of climate modeling, the realm of equations. So here, no observations are involved. Okay, so no observations here are involved. These are solving climate models that are about solving PDEs. You don't use data from observations when you develop your model, your climate model. Probably this is not maybe not clear enough. So again, climate models are like computer simulation, where you start from some initial points. You do have some equations, and then you integrate in time. That's it. You see what I mean? So there is no external data. Yeah, depends here. It depends if you want actually to do a very long time climate simulation. You can do with a specific time step-in. In general, it's a short time step-in. In general, it's some minutes, for example. And for the initialization, it depends on which field. The wind is initialized differently than temperature. So there are a lot of choices here. Okay. So yeah, I'll get to there. So the idea was, the question was how to use the clusters for the SimPlex models, okay? So since she already found these clusters and validated them using physical knowledge, actually what I suggested to her is to take these clusters as ground truth and try to emulate the k-means here, okay? So instead of using the 5 terms which are not accessible using SimPlex models, we use different inputs, that's the B step, different inputs that are actually accessible from the SimPlex model, and we trained in a supervised this time learning way, a neural net, or can use random forest or other to predict the clusters. So this is now a classification, a classical supervised classification problem. And when you get, when you finish your training, you now have an emulator for the k-means, okay? So of course, this is not perfect. Yeah.
Where do you get the data? What are the labels?
Yeah, the labels actually was the results of the k-means from the last paper.
But then why don't you just learn to do the same thing? Why do you
yeah, because actually you cannot find the 5 terms for the SimPlex models. That's why. There are some physical reasons and computational reasons also that you cannot, calculate the same 5 terms for the other SimPlex models I want to use my data on. So that was really the reason, because if you could have the 5 terms, there's no need. You can use k-means again, and that's it. Okay. So so then when we trained our neural net, we could use it for different SimPlex models, and we got this question also of estimator uncertainty, because if you can rely just on one neural net, that would not be perfect. Sometimes actually you can just change the initialization of your neural net and train it again, and it can give you different predictions. So actually having an ensemble, and this is quite classic in machine learning, using an ensemble of neural net can help you to actually estimate an uncertainty for your classes. One thing I wanted to mention also is the use of XAI techniques. I won't take a lot of time on that part, but that was one of the most important actually contributions also, because in climate science in general, they always ask, to open the black box to explain actually the prediction of your neural nets or other machine learning techniques. So we use the classical technique called LRP, okay, to do the explainability of neural net. And the idea of LRP is very simple. You have your output, okay, and in a specific, for example, class, you want to know what are the inputs that were most important for your classification, okay? And then you have a set of rules that takes the output of your neural net and distribute some scores to each layer of your neural net until the input. So you get some scores for the input. When the score is positive, this is indicating that the input was actually pushing pushing right to the class, and if it is negative, it's the opposite. So it's more relevant if it is positive, and it's actually less relevant or not relevant at all if the score is negative. So we use this, with, of course, again, the help of physical scientists, and they actually interpreted, and all of this is the paper. In the paper, each class we found what were the inputs that were very important for the classification, and also some physical interpretations of why this happens. So that was really interesting. I did not, of course, participate in that physical interpretation part, but it was really interesting to see.
So maybe you already said that, but your network, was it trying to predict the colors, so the categories as hard things, or did you use the weights coming from the k-means?
Actually, it tries to find the classes, okay?
Sure,
but the ground truth, yeah, the ground truth was from the k-means. That's the thing.
You use the weight from the k-means. So when you do k-means, you belong to a class, but you belong to, you have different weights to different classes.
Yeah, that was hard.
Like
that actually was hard k-means. So each point actually goes to one class. It was not a fuzzy k-means or. Yeah, but that's a good actually remark. We could worked on a fuzzy k-means that can give you a percentage, yeah, for this class and a percentage for another. Yeah, that's a good remark. Yeah. There's another question. Yeah, here for the inputs, these are maps, 2D maps. 2D maps. Yeah, nothing special about it. No, we do some. We calculate means, actually. There is a bathymetry map, and we use that also actually to represent the depth. So maybe I'll skip this slide, but this is actually one of our students who was from the Bronx Community College, and he's now in Stanford, that took this technique and applied them to several CMIP6 models, okay, the French one, the American one, and others. And he worked also on the interpretations of what was happening. For example, for the historical scenario, the historical scenario is the one that corresponds to observations. And the 4 multiplied CO2 is the scenario where we add CO2 in the models. And we saw how the clusters actually shift a bit to the north. So this also was actually explained in another paper. So if you are interested, the code, of course, is open source. We got a spotlight also talk at Climate Change workshop in ICLR, and with another collaborator from ECMWF, we published a Bayesian neural net version, because you saw we used the ensemble MLP, and we were curious to know if you used a Bayesian neural net version. Well, we were actually assured because the classes were quite the same, okay? But it was interesting actually to see with the Bayesian neural nets how the training was done. Okay, donc, so the last part, this is a different application, and you'll see actually how machine learning can be used in post-processing, but now really in model development, in pure model development. So here the idea is to try to tune a model, and this is, quite closely related, for example, to hyperparameter tuning, when you try to actually find the hyperparameters of your neural net, okay? But with some climate model tuning by hand, which is done currently by most of the climate modeling centers. The idea is you do have some parameters that you need to tune, to specify, to fix before running your simulation, okay? So what happens right now, I mean, currently is that you do have physical experts. They do have some intuition. So they know, for example, that the parameter, let's say alpha is between -10 and 10, the parameter beta is -1 and 1, etc. And with their experience, they can like fix some parameters and run the simulation and get the results at the end, compare them with the observations. If they are good, that's it. If not, they come back, okay? They come back again, they tune again, they run again. And of course, this is a process which is very, very expensive, especially when you know that sometimes you need to wait a month to get your result. So this is, yeah, try and error process, computationally expensive. So what can we do? We can actually try to use ideas from surrogate modeling, okay? This was actually a project from the Maker Plan Göttingen project Hermes. My collaborator Julie from CNRS and V. Balaji from Schmidt Future. The goal actually was to use emulators to try to accelerate this search of parameters, okay? So for if you want to get an idea, for example, for the IPSL model, the latest one, it took 5 years to find an acceptable tuning to really measure why this is a crucial problem. So if ideally you did have like infinite computing power, what you have probably done is try every combination possible of parameters, but you can't, okay? Because climate models are again expensive to run. So you can actually use two ideas from different communities. The first, since you have some priors, okay? You have a hypercube, hyperrectangle of your prior, okay? For example, if you have 3 parameters, you have each parameters up an interval, okay? And you have a cube, and you want to explore this cube, okay, of parameters. What you can use is techniques from space filling designs. Space filling designs, the idea is simple, try to cover the whole space with few samples, okay? And one of the techniques which is very classic in that field is latent hypercube sampling. I can get to it later. But yeah.
What's the score function like when you, let's say, you did some random sampling? What is the
yeah, here actually just for the space filling design, it's for the space filling design, it's maximizing the minimum distance. Okay, you want actually your point to be very far from each other, okay, but to cover the space. So there is a version which is called Maximin LHS. But then for the other metrics for the climate models, I'm coming to them. And the second ideas you can use is ideas from surrogate modeling, the use of emulators, okay, instead of your very expensive climate model. So the algorithm of history matching, which is again an old algorithm, exists in the literature that was used in epidemiology, in cosmology, but not a lot in climate science. It was used just for some component of climate models. The idea is the following. So you do have your initial guess of parameters. Again, for example, alpha is like between -10 and 10, etc. You use an LHS to get a few number of representative samples from that space. And this number of representative points, you can use them to run your real climate model, okay? This is actually to build a training data set, okay? But you cannot run millions. Here we are talking about tens of simulations. That's what makes it very hard to use in climate modeling. So when you finish running your very big, complex, coupled model, you calculate some metrics. The metrics, when we talk about metrics, and that's your question, actually some metrics are, for example, the temperature, the mean temperature in a specific area in a specific year, or for example, the position of the Gulf Stream if it is very far from the continent. So there are some specific metrics chosen by the physicists. And of course, here the question is, yeah, you tune for these metrics. Okay, so this is dependent on the metrics you use.
What's the ground truth? Like, what do you consider?
Well, the ground truth here, I mean, is observations. Is observations. Because you at the end, the metrics are like distances to the observations. So when you have your training data sets, the training data set is inputs. Yeah, so.
So if I understand this correctly, the idea is you have, I guess, like certain parameters that you need to tune. Typically, this is done by a person, but you don't want to run a very expensive simulator every time, so you can an emulator and do this. So how many parameters do you, how many, I guess, like choices of parameters do you expect to match historical observations? And of the ones that match historical observations, how many of them are sensible enough to collect?
Yeah, that's an excellent question, actually. And there are a lot of works specifically on that question. First, on the number, how much actually samples you need to do this emulation strategy, and also what are the inputs that are really, really relevant for the metrics you are training for. So there are like some sensitivity analysis, done before to select actually the inputs that you want to tune. And this is in general, to be honest with you, in general, the physicists come and say, yeah, in my experience, these parameters are the ones that are really affecting the climate simulation, you see? So the list of parameters, they actually choose it. But you can do it automatically.
So
you can do it automatically.
You can imagine a scenario, right? Like there's one 10 list of numbers that a physicist say this is good.
Yeah.
Another one that's physicist B. And then like, now we're changing the paradigm a bit to build an ML model.
Mm-hmm.
And they could have, this could spit out, right? Like 1,000 possible list of 10 numbers that, I guess, like fit observational data. I guess, like, how do you know of the like 1,000, other than, I guess, going back to a physicist, which one would give you a reasonable projection of future scenarios?
Yeah, this is we didn't explore actually. That's what, we didn't explore actually this because, again, we go back to the physicists. They give, we don't want like to throw out all the physical intuition. So we start by, doing, small steps, working with physicists and trusting their knowledge. And then when we have like a good model, tuned model, we can then think about how we can, use maybe the inputs or the parameters that were not tuned, add them again and run again this tuning process. But now, yeah, it's really, this is still in the beginning. It's still really in the beginning, what I'm showing you here. It's this year, started from last year. Yeah, of course.
This is out of distribution, like sort of when you want to do these predictions, like to me almost like World Cup projections. Like
you think?
It's different teams, different players. Because it has human in the loop, right?
Human in the loop, not too much. Okay, human in the loop here is more on the input parameters you want to tune and the metrics. Okay, but a lot of the job is done by the emulators. But yeah,
human in the loop. That this projection highly depends on basically what humans do during the 60 years.
You are asking a completely different question. So here, actually, we are trying just to match the observations, the historical ones. Okay, that's it. We don't try with scenarios. So yeah, but actually, it was a good question because I was thinking about the human in the loop, because actually physicists are still involved. The ideal way was to use an automatic technique and do the tuning without needing a human. But they want to be involved. That's the thing they want. Yeah, they want to be involved to be sure and to trust the results. All right. Yes.
Yeah. So if we remove the simulation with surrogate modeling, this is maybe classical parameter classification techniques.
Yeah, parameter estimation. Yeah.
Now we are adding another one layer with this emulator, which has also some parameters. So can we do all at once?
Yeah, actually, that's what we do. Yeah, we estimate the parameters of the Gaussian process, and this helps you to estimate the parameters of. Yeah, but you can see it as a parameter estimation problem. The thing is, the model is very expensive. That's why we use emulators. But yeah, it's a parameter estimation problem.
Can you give us some examples of these parameters? Is it the size of a grid?
Not really. Well, I cannot give like specific, but sometimes it's like a coefficient for viscosity in a fluid, or some specific, choices for an equation. For example, there's an equation and there's a specific parameter in it, which is constant, and they need to choose this constant. So these are like, yeah, exactly. Yeah, with the equations, you do have a list before running your code, a list of constants, for example, you need to fix before running the equations, before integrating the equations. Okay. All right, so I'll try to be very quick. I don't know how much time I do have. Maybe I'm already.
So there are 10 more minutes, but after that,
okay.
There is a session.
All right, so all right. All right, I'll be very quick. So yeah, we train Gaussian process regression. Why? For two reasons. Gaussian process regression can work well with few data, and also it gives you uncertainty. Okay, so that's the main reason, and we do need the uncertainty also to calculate what we call the implausibility, which is some sort of distance with the observation. Okay, so each combination of parameters is run using the model, the climate model. Then we train the emulator, and the emulator is quick. You can run on GPUs. You can run millions of combinations to get your to actually interpolate the search space. All right, and then there is a rule to keep the good parameter space and rule out the bad parameter space. All right. This is another strategy, because there is the strategy of Bayesian optimization, where you are trying to find the posterior, the posterior distribution of your parameters, but it will always find you a solution because it needs to sum up to one, okay? But here in our cases, we are not sure about the model. Maybe the model is not really good. So we want, before that, to remove the bad parts of the parameter space before trying to really find the optimal solutions. So I did try that on the Lawrence 96 model. So no need to, again, get into details, but these are like a couple of equations, which the X, for example, is for slow dynamics, and Y is for fast dynamics. It's like, the ocean and the atmosphere, because the atmosphere is very fast, actually. The processes are very fast in the atmosphere, and they are very slow in the ocean, and they are coupled, okay? There are exchanges between the ocean and the atmosphere. So this is a toy model, a simplified version. And the parameters I wanted to tune are H, C, F, and B. You will see them in the equation, okay? And what you see here is the result of history matching in waves, because you can do it one time, reduce the search space, and then do it again another time, and again reduce the search space, okay? Because you can train better emulators when you finish each wave, let's say, of history matching. So you start, let's look just at the lower triangular part. We start with the 4-dimensional space. We cannot actually plot a 4-dimensional space, so we plot several 2D images, and then the parts that are red are the parts that we move from our search space, and we keep just narrowing the search space until you see the fourth, this one, that we have really narrowed a lot the search space. Since here I'm already, I know already the good parameters, I did put them as black points. So you see, we did not rule out the good parameters. We really narrowed with history matching to get to these parameters. But what is interesting here, they are not the only ones. You still have some space of like good solutions too. And that's what climate scientists are looking for. They are not looking at one specific good model, but they want actually a range of an ensemble good models so that they can do uncertainty quantification and also not rely only on one specific model every time. So this is, yeah, this is just some details. Yeah, of course. What it,
have one single model that has very high certainty, would you still need to use an ensemble and like explore their certainty?
The thing is, yeah, the thing is there is no perfect model, and it's impossible, nearly impossible to get it. For example, climate models nowadays, some of them, for example, are good for Europe, but not good for Africa. And some of them are good for United States and North America, but not very good. There are biases, and the biases are not, I mean, homogeneous on the globe. Some biases are in some regions. And so we need, I mean, for now, we need always to have an ensemble of models, to not rely on one ensemble. So that's why in CMIP6, we have like ensembles of models from more than 40 climate modeling centers in the world.
So basically that ensemble of models is your universal model.
Yeah, exactly, yeah, exactly. That's what we use for the IPCC reports. We use, for now, we use a mean, but the mean is not really a good choice. I mean, there are people working on a weighted mean because it's like a democratic choice. This is a bit, it's a democratic choice. You cannot say no, models from, I don't know, this country, we will not use them. So that's why they use a mean for all the models. But now scientists are starting to say, no, this is not possible. We need to put more weights for the best models and less weights for the worse models. Okay.
How do we know?
Well, there are papers. No, actually, that's a good question. There are papers that, for example, focus on North Africa, and they say, yeah, these models are good for North Africa. Those are not good for North Africa, but they are not. I mean, they're not the worst for every region in the world.
So these 50 models,
yeah.
Do they implement the same equations? They model exactly the same, the ocean, the atmosphere,
Yeah. But they have some specific choices, specific tunings, and also in the numerical methods, they are not the same in general. For example, some use third order integrating numerical models, some others use other techniques, some others do spatial differentiation, and some others use Fourier, they go to the Fourier space. So there are some choices in each of the, yeah. But the equation, Navier-Stokes equation, some simplification of Navier-Stokes equations, all of them are using the same. Okay, so I'll just skip this. And this is the paper. This is the paper is still in a revision, but there are, I mean, a lot of other papers on history matching, specifically for the atmosphere, for example, or specifically for the ocean. What I'm trying to do here is to try to do it for a coupled model, not just for specific components. So yeah, I think that's the end of my presentation. I have some very, quick lessons I learned with you here, and actually, my experience is the same. When you do AI4Science, you need to incorporate as much domain expertise as you can. You cannot just like come to replace physical scientists. You need to involve them and to attract them and to validate your results with them. And actually, this is more one of the comments I gave to in a presentation for a pure scientific, pure physical community, that they need actually to be patient and open mind when they collaborate with machine learners. Okay, so we cannot like say that, for example, this machine learning model is maybe very good, but they cannot use it. They need to say why, not just resist without a justification. So now things are getting better. Now they ask for justification. They actually, for example, encourage you to use XAI techniques and to interpret your results. And also techniques that combine physical knowledge and machine learning are increasingly popular, even in climate science. I saw this in this conference. And yeah, there is a call for climate scientists now. I mean, even for the journals of machine learning for climate science, now they ask always for like parts where you interpret your results, either using interpretable AI or explainable AI. Interpretable AI is pre-developing your technique. Explainable is when you finish and you have your box and you want to explain your machine learning model. So yeah, last some advertisements for some future events of interest. I was thinking about students here. I'm a co-convener of a session, machine learning for Earth science system modeling in Vienna. So there's a deadline for abstract if you are interested. I'm also a member of the scientific committee in Liège, Belgium for a machine learning and data analysis conference, but especially in oceanography. And also I'm a co-founder of Morocco AI, non-profit organization. If you want more detail of any of these events, please come and see me. And thanks a lot. This is a review paper I wrote recently on machine learning for oceanography, but it can give you some ideas of applications. And thanks a lot. I'm sorry, I took maybe too much time.
Are there any additional questions?
So I have a question. We had yesterday a presentation about physics empowerment neural
Yeah.
Are one of the models today that are used in this community using?
Yeah, nice question. Actually, I enjoyed the talk by Maziar yesterday. The pins, for example, are used for solving some PDEs. And in the climate models we have, there are specific PDEs in some parts of the code, okay? Some inversions, Poisson equation, for example, Helmholtz equations and other equations. Those are opportunities where you can use, for example, pins. But there are like some challenges which are not scientific, but more on the code. For example, how to train a code in PyTorch and put it in Fortran. This is quite, there are some solutions now. There are some people from Oxford, I think. They developed a way to create a bridge between, for example, Keras and Fortran. So you can like train your model on Keras and then translate it on Fortran code. Okay, when you finish your training, of course.
What about the whole Navier-Stokes, maybe
the Navier-Stokes, for example, he showed yesterday. It was very simplistic, I think, for our presentation. You know, there are no works. I can't tell you this. No, there are no works. I mean, trying to replace a climate model with a pin. No, because I think there are a lot of difficulties. That's why. But for small, for specific components, that could be a good thing to do.
If I understand well, the climate model are very big codes
Yeah,
that have
big
been
code.
built. So it's like there are threads.
Yeah, components
and
components, ocean components, atmosphere components, ice component, and then coupling everything.
And so nobody tried to do a new model based maybe on using AI.
There are some
from scratch. Using
yeah, there are some tries. Yeah.
It's also a very old language. So
Yeah,
maybe there
yeah.
are new versions. I don't know, but because I remember Vincent Echevin,
Vincent.
who worked with me. He was already using Altron, but like 30 years ago. And it's really strange for the.
Yeah, it's still used, Fortran. Yeah, it's still used for some parallel computing capacities also. But yeah, there are some tries, but it's still in the papers. I mean, it's not operational.
Really a climate model with
Yeah, they are
AI
trying. Yeah.
Inside it, is it something which is being developed right now?
It's being developed right now, for example, but it's still not operational. It's still, I mean, in research stage. There is a group, for example, in Georgia. No, I don't remember. The name is Clima. They are in the United States, and actually, what they are trying to do, it's quite clever, writing from scratch a model, but using, for example, Julia. It's another language. Well, again, it's another language, programming language. But with Julia, you can do automatic differentiation, for example, and use a neural net inside and train end to end. Okay, but they're still, I mean, working on it. They started like 2 years ago.
Okay. Are there any questions? So there is the poster session now in the hall. And so I invite you all to go and discuss with the people presenting their posters. And the coffee break is also in the hall. So you can at the same time think and drink coffee.
Thank you.